Sup, AP? Let me remind you that our AP exam is coming up on May the 7th. I know that's early, but that's just the way it is at 8 a.m. And I'm still making sure that it's on campus, okay? If we miss this date, there is a retake, which will be fully digital on your own on June the 2nd. And what that means is there are more FRQs on this paper-based test for campus, and there's more multiple choice on this one, right? More multiple choice. But I'm pretty sure that the school has paid for this one, okay? And I'm pretty sure that you and you will have to pay for this one. So let's make sure that we get that in order to be there for that exam. So let's continue our concept, our conversation, and our big idea of chemical equilibrium. And I always spell this wrong. Equilibrium. Okay, so chemical equilibrium, as we discussed, has many real-world examples as far as keeping us alive, refrigerating our food, pressure, different things like that. And scientists have figured out how to really speed up and create and use the process of equilibrium to help us in everyday life. Let me say, first of all, that every reaction is really an equilibrium reaction. Every reaction. Now, that doesn't make any sense because most of the time in chemistry, we use a simple concept of equilibrium or simple concept of reactions that kind of go like this. A plus B yields, right? Yields C, and then plus D. Now, this is a overgeneralized reaction, but we know this as a simple forward reaction, right? Where the reactants are producing the products. Okay, we know that as that, and that would look like this in on a chart where you are saying over time the concentrations are doing this. So basically, you start up here with your reactants, and you move forward, right? Move forward, and you got some activation energy with a hump. Comes down here, boom. And we know this as an exothermic process, right? So over time, you have this process of movement, right? And remember, just as a refresher, this is called the activation complex, right? Or the transition state right here. And this is called the activation energy area. And this is how much energy it's going to take in order to make this process happen, okay? And this is how much energy is going to be released, the difference between here and here. That's how much energy is going to be released. Now, if you look at this, you will see that the way this is written is that most of the products, since the activation energy is lower on this side, is going to be able to get over, and not as much is going to be able to get over, going in the reverse direction. And so usually when we think about this, we think of this straightforward reaction because these are the graphs we look at. But in reality, the graph will look like this. Not as much activation energy, and we'll kind of reverse the colors there, but the reaction would look something like this. So you got starting here at a certain concentration, right? And over time, the reaction would go, and you got activation energy, but it's going to be a little less than this one, right? It's going to be not as much, right? But you still have this process. Now, if you notice, this is going down as far as the reaction. So this is still an exothermic reaction because it's releasing, right? An exothermic reaction because it's releasing. And so you have these products that are moving, boom, boom, boom. But you can see that they will also be able to move back here. Now, that also tells us that maybe not the amount on both sides will be the same, because some of them won't be able to overcome this more activation energy and reach the activation complex. But for the most part, we will be able to get some going forward and some going backwards. And in process, this is the concept of chemical equilibrium. And let me give you a definition for chemical equilibrium. Chemical equilibrium definition is this. So let's change the color so that we can actually enjoy it. Chemical equilibrium, I'm just going to express it like that, chemical equilibrium. That is the defined as when the rate, remember that, chemical kinetics of the reverse action, and remember, rate deals with what? Rate deals with concentration, molarity. When the rate of concentration of the reverse action is equal to the rate of concentration of the, I'm going to put an A here, okay? It's in molarity, but I'm going to put an A and a B, is equal to the rate of B, the forward reaction, okay? And so basically what you have here, and this is the sign for it, you have a reaction that is going, and we'll use the Haber process again. You got N2 plus 2H2, let's make it 3H2, yields for us 2NH3. Okay, so we have this process where the rate of this concentration, okay, is going to be moving, the rate of this process is going to be moving as fast as the rate of concentration of this reverse reaction. I should have put that up here, A and B, okay? Actually, this would be A. This would be B. So you have this rate of reaction. Now that does not mean that you're going to have the same amount being produced, right, on each side. The same amount is not going to be equal most of the time. Sometimes it can be, but most of the time it's not. But what we're talking about here is the rate of the reverse and the rate of the forward reaction. What that means is that at some point in the chemical reaction, that the rate of concentration raised to some power is going to remain, and B, right, B raised to some power is going to remain the same. It's going to reach this place where it remains the same. And so next video, we're going to talk about the difference between the concept of static equilibrium and dynamic equilibrium. So hopefully that led you into a process of what chemical equilibrium is all about. It's all about, let's just refresh real quick, it's all about the rate of the forward reaction being equal to the rate of the reverse reaction. So that's what chemical equilibrium is all about. Not the amount, but the amount of concentration. Not the amount of products and reactants, not the same number of them. You're not getting 3 of these and 3 of those, 3 of these, 3 of those. You might get, on this side, you might get 4. And you might get 3, and you'll start with 0 and move to 4, and then you might go to 2 and get to 6, and then you might get 2 and move to 4, or 3 and move to 4, and then you might get 3 and 3, and like it's not the same amount, it's the speed or the rate of concentration change is becoming equal.